Which one?
Yeah, 30 is fine.
Which one did you have in mind?
I'm going to say 28, but it's probably not that much.
Okay. 30. E to 2x minus e to x minus 6 equals 0. Good. Okay. Remember, we have to look at the big picture, and then we have to look at the small picture. Okay, so let's look at the big picture. When I look at the big picture, I do not see e to the x or e to 2x. I see what?
Numbers.
Say it again. Okay. Joey, you said something?
It's an exponential equation.
I agree. It is exponential, but not pure exponential.
Right.
Right? Because a pure exponential function has something with exponent on one side and a number on the other side. But this one has 3 terms.
Right.
So once I see 3 terms, I'll say, I do see some exponential in there, but not pure exponential, and it's combined with something else. What is that something else? If it has 3 terms. It appears to be quadratic. So exponential and quadratic together, what would I think of immediately? Maybe it's quadratic in 4. So I'm going to say let y be,
E to the x.
because if this is y and if the first term is
Same base.
right,
It'd be y squared.
yes, if this is y and if this one can be replaced by y squared, otherwise I cannot say it's quadratic in form. So if I square this, do I get this? If I raise this to the second power, do I get this?
Yes.
Then it's quadratic in form, and I am on the right track. And then the new equation is
Y squared minus y minus x equals 0.
which again is much easier, more human to deal with.
Yeah.
So the key is, from what we've learned so far in this semester, is to be able to identify things now. I know we had a lot of different things we looked at. So then this I know how to, right, so I have y minus 3 and y plus 2, very good. And there are 2 options for y. I agree, y equals
3 equals -2.
good. So now the equation y equals 3 is actually what equation?
E to the x.
Now this is exponential, and it's pure, and I know how to handle it. And the other option is,
E to the x.
I should have written y equals -2, sorry. Okay, so let's start with the first one. Now this is nice and clean, it's pure. However, e and 3 will never be written with the same base, but I have a cure for that. And which base exactly I'm going to apply? Yes. So then I have x equals natural log 3, because I bring x down and natural log e is 1. So this is my first answer. Then I have to look at the equation e to the x equals -2. How will you handle this? Right. Careful.
No.
Yes, the answer is O.
Is it negative?
Because exactly.
Yeah.
Can I apply log to -2?
No.
No.
Greater than
So remember, this graph is this.
Yeah.
Where is -2? Here.
Yeah.
Where do they intersect? Where does -2 intersect e to the x?
Yeah.
It doesn't.
So you only have one solution.
Exactly. Impossible. And yes, it's not a mistake to say, well, the equation has no solutions because I can apply log to the left-hand side, but I cannot apply log to the right-hand side. That's good enough. So the equation has only one solution. Okay, let's move on to logarithmic equations now. Log equations. Well, log equations are not as friendly as exponential equations. Why? Because log is not a friendly function. Why? Because log is not defined everywhere.
Restrictions.
Exactly. You have two options here. When you solve logarithmic equations, you have two options. I'm not enforcing any particular method. I prefer to state the domain because I tend to forget to go back and check. But you may say, I don't want to state the domain. But I promise to always go back back to the original problem and check anything I get. 1 solution, 2 solutions, 5 solutions, I have to go back and check. It's up to you. But you have to. And you have to choose one method or the other. You don't have to be consistent. On problem 1, you can state the domain. On problem 2, you can check the answer. It doesn't matter. But you have to remember that you have to apply one or the other. Okay. Let's say 52. On page 338. Log x plus log x minus 3 equals 1. Okay, what type of equation is this?
Log.
Yes, it is log. What is the domain? What do I have to write? What is the restriction for this to exist? I have to write that x, exactly.
Minus 3 is greater than
And x minus 3 has to be greater than 0. In other words, I'm kind of stating the domain as the common domain. If I had a function in x on the right-hand side, I would have included that too. But this is just a number. So I only have a function created by summing of 2 log functions. So then this means x greater than 0, and this means x greater than 3. Where's the common domain? Okay, let's graph it. Negative infinity to infinity. Here is 0 to infinity. And here is 3 to infinity. I need to choose the territory that makes both functions exist at the same time.
That's greater than 3.
So 3 to infinity. Good. So if I do not find, when I solve this equation, if I do not find a number that is in the interval 3 to infinity, not 3, then I will say the equation has
no solution.
no solutions. Now that's the reason why I learned how to condense logs. The left-hand side has to be condensed. You cannot state the domain after you condense it. The domain will be totally different. So if you state the domain, you have to state the domain on the raw equation. Okay, so please condense the left-hand side for me.
Log x.
Yes,
X minus 3.
perfect. Equals? Now I want to change this into what? Exponential equation. What is the base here? I don't even see a base.
10.
10 raised to
1.
equals?
Oh, that makes sense.
Yes. So 10 raised to the first power equals x squared minus 3x. I already distributed. So what type of equation is this? No, this one.
Right?
Yes. So x squared minus 3x.
That's nice.
Right. Because we know from a long time already, right, that quadratic equations require us to set them equal to 0. Unless specific cases happen when I want to take the square root and so on and so forth. Good. What do I do next? So then x equals 5 and x equals negative 2. What do you think I'm going to do next? Correct. Yes. I don't have to go back from back to the original problem because I took the time and I stated the common domain. So now I see this one is okay and this one is not, and I'm done. I have to be honest and say sometimes checking will be easier depending on the expressions. Because this may be, for example, a rational. Instead of x minus 3 can be a rational expression, and you have to use the table to find the domain.
Mm-hmm.
So it depends. As I said, you have the flexibility of changing. Okay, please choose anything you want. From 37 through 54. And then I would like to look at a word problem. Which one?
Does it work?
I'd like to look at the fish population after that. Look again at the applications of exponential and log. Fish population. This is a logistic growth model. Look at the cooling of an engine. It has a natural log in it. Electric circuits. SEC has an exponential in it. Just everywhere. And then I like to look at exponential decay. Exponential growth and exponential decay. And that's the end of chapter 4. Okay, which one? Okay, 50. So in 50 we have log base 3 of x plus 15 minus log base 3 of x minus 1 equals 2. Okay, assuming you agree with me and you will state domain and find the common domain, what will you write for the first function?
That's plus 15 greater than
What will you write for the second one?
x minus 1.
Good. So then this one has greater than negative 15 and this one greater than 1. So what will be this? What is called the common domain? Exactly. So if the solution or solutions I get are not numbers greater than 1, I'll say, sorry. Is this okay, Nico? Okay. Everyone? Okay. So now on the left-hand side, how do I condense the left-hand side?
Log base 3 plus 15 over x minus 1.
Now, I can change it into an exponent. I couldn't have without condensing it.
Mm-hmm.
Because it has to be a simple log equation, so I can condense it. I can change it into an exponential. So what do I write?
X plus 15 over x minus 1 equals 6.
3 squared, right?
Yeah.
3 squared equals x plus 15 over x minus 1. So 9 over 1 equals x plus 15 over x minus 1. I specifically wrote 9 over 1. Why?
Proportion.
Yes. So I cross multiply. So I have 9x minus 9 equals x plus 15, or 8x equals 24, or x equals 3. Of course, with a question mark. And you'll tell me whether it's acceptable or not.
Yes.
Acceptable, yes. Because it's a number greater than 1. And we took the time to determine that. Okay, very good. Before we look at the last section with the major applications, I'd like to look at this. It caught my eye. The fish population. A small lake is stocked with a certain species of fish. The fish population is modeled by the function, where p is the number of fish in thousands. So here they are telling us thousands. And t is measured in years, since the lake was stocked. Okay, find the fish population after 3 years. After how many years will the fish population reach 5,000? So 83 on 339. So p equals 10 divided by 1 plus 4e to negative 0.8 t. Now, I think it would be nicer if they have put something like this, p of t, so we know. So p is the number of fish in thousands, and t, number of years. So t in years, and p in thousands. And part A, p of 3. Now, when you look at this function, you don't need to know the name of it, but you could say it's a combination of a rational function with exponential. Okay. It's a logistic growth model, actually. Okay, so here it is. So 10 divided by, in parentheses, 1 plus 4. Here's e, careful. E is right here with natural log. I will put it in parentheses its power, negative 0.8. This negative here, the sign, negative 0.8 multiplied by 3, close the parenthesis for the denominator, and then press enter. So I'm looking just to make sure that I copied everything correctly. 10 divided. Okay, very good. So 7,337,000. 7,337 fish. Okay, part B. After how many years will the fish population reach 5,000 fish? Of course, they want to be, yes, they want to be tricky here. So P equals 5, which basically means 5,000. Good. So we're asked to find when. How would you start?
My log.
Yeah.
Well, I guess you write the equation.
Yes, I have to. Yeah, yes, but since this is the trick here, it says P in thousands.
Yeah.
So I cannot put 5,000, but I have to write 5.
Right.
For P. Okay, equals 10 divided by 1 plus 4 e to negative 0.8 t. You understand I cannot apply any log or do any of that yet.
Right.
Log is applicable only when I have one piece of exponential expression on one side, just one, no ratio, no nothing else,
Okay.
and a number on the other side, not 0 and not negative. Because if it's 0 or negative, I cannot apply log to it. So is that clear?
Mm-hmm.
Okay. What do I do?
5 over 1.
Yes. And then?
Plus multiply.
Exactly. First, I do not see the exponential part. First, I see the proportion part.
Right.
So I have 5. 1 plus 4 e to negative 0.8 t equals 10. What now?
Divide by 5.
Very good. So 1 plus 4 e to negative 0.8 t equals 2. I divided both sides by 5. Very good. So 4 e to negative 0.8 t equals 1. I subtracted 1 from both sides. Exactly. E to negative 0.8 t equals 1/4. Only at this stage, I will consider applying what to both sides. Right. They always remember, factors simplify, but also what we like to say, clean it up. Clean it up to the maximum before, because you're going to make your life easier. So then the left-hand side, I apply natural log. Two numbers are equal. Their logs must be the same, in the same base, of course. So negative 0.8 t equals natural log 0.25. Or just keep it as 1/4, it doesn't matter. Okay, finally t, negative natural log 0.25 divided by 0.8. We're talking about time. What should the answer be? Right. And definitely, let's think for a moment. Careful, because when we plugged in 3, we got 7,000. So now we want 5,000.
Plus 3.
Less than 3. Very good. Okay, so what am I doing? I have negative natural log 0.25, close the parenthesis, divided by 0.8. So it's 1.73 years. So t approximately 1.73 years. So according to the model, it appears that in about 1.73 years, the fish population will reach 5,000. Okay. More of the same. There are two very important models that I would like to emphasize. And then we'll look at all different problems in your book. So the exponential growth model and the exponential decay model. We normally use two different notations. Those two models are very similar. We normally use two different notations. The exponential growth model is normally uses n as the number of bacteria, number of the population, number of bats, number of mice, number of rats, number of rabbits, number, n. So it's n of t. It's a number.
Right.
It can be bacteria, it can be number of population. The exponential decay model normally deals, I shouldn't say normally, but one of the most popular applications here is about radioactive substances. They decrease their massing time, so that's why the model is m of t, not n of t. N stands for number, m stands for mass. What are these models? And you will see the similarities. N0 and M0. What would be N0? Anything with sub-zero deals with initial number. Anything with M0 will be initial mass. Okay. E and E. RT and negative RT. And this is exactly the same with the model that we looked at last week with A equals P e to RT. As you see, they're all the same. The only difference is here. Why is this? Because it's decay, and this will be a base less than 1, because it will be e to negative 1 over e. But all these are basically the same. This was the accumulated value, the principal for the interest compounded continuously. So these are all pretty much the same. So now let's look. Before we look at any of these models, here's a question for you. Let's suppose we are told, and I'm going to find a problem like that. Let's suppose we are told that we have in the building a mice population. And they are telling us that the mice population doubles every 7 days. What does that mean? It means that if today we have 10 mice, we will have 20 in 7 days. Okay, I'm here now, and I have 20. So in 7 more days, I will have 40, and so on and so forth. Okay, stay with the idea. What if we say here, well, that's not the case. Let's say we have 100 milligrams of radioactive substance that has a half-life of 10 days. So let's say I have 100 milligrams today. In 10 days, and in 10 days, good. Okay. Okay, on page, I like to start with cooling a soup. No, I'm not hungry. But cooling a soup, 25. And this is page 352. And this is all these exercises here. Use Newton's law of cooling. You don't have to memorize any of that. The formula will be given to us. We just have to answer a couple of questions. If you remember, I said Newton's law of cooling is used for finding the time of death for someone who died. Okay? And cooling a turkey, if you remember, we talked about that. I said this is one of the typical examples in this with log and exponential, and so on and so forth. So let's start with the cooling of the soup. Just a simple warm-up problem. 25 on 352. And then we'll look at those models. A hot bowl of soup is served at a dinner party. It starts to cool according to Newton's law of cooling. So its temperature at time t is given by. Temperature at time t is 65 plus 145 times e to negative 0.05 t. I hope you find this easier than, let's say, trig equations. Okay. First question. And by the way, they're all the same idea. They all follow the same pattern. T is measured in minutes, and uppercase T is measured in degree Fahrenheit. So this is in degree Fahrenheit, and this is in minutes. What is the initial temperature of the soup? What am I asked to find when I'm asked to determine the initial?
Time 0.
Exactly. So T0. Yes, you're right. We will be still the same thing. So when n is 0, this will be 0. R times 0 will be 1. I'm sorry. R times 0 will be 0. E to 0 will be 1, and then I'll get n0 when t is 0. So, negative 0.05 times 0. E to 0. 1. 1 times 145. 145 plus 65. So the soup was warmed up to 210 degree Fahrenheit, according to the model. Part B, what is the temperature after 10 minutes? And after how long will the temperature be 100? So 65 plus 145 times E in parentheses. It's times 10, so it's negative 0.5. Close the parenthesis. 152.95 approximately. Any problems so far? Pretty easy. Okay. After how long will the temperature be 100 degrees Fahrenheit? 100 degrees. What do I have to do?
100 equals 65 plus 1.5.
Of course, I'm going to remove these from the equation. So I want to apply log to both sides.
Okay.
Of course not. It's not cleaned up. And
65.
when I'm exactly, and then I have to get rid of this.
Yeah.
So it has to be pure exponential on one side, make it ready, clean it up, so I can apply log to it. So 35 equals 145 e2 negative 0.05 t. 35 over 145 equals e2 negative 0.05 t. Only now I'm ready to apply natural log to both sides. Two numbers are equal, the natural logs will be the same. Mandatory. So the negative 0.05 t equals within the graphing calculator. So we have the top, natural log of 35 over 145, and then divide by, in parentheses, negative 0.05. Thank you. Okay, let's see what I did. Ah, we got it. $28.43. What is that? Yes. So roughly the temperature drops from 210 to 100 in roughly 28.43 minutes. Okay. Good. Let's look at population of, so let me ask you what would you be interested in? Bacteria culture, population of California, world population, before we look at radioactive decay. Bacteria?
Say
Say it again. Oh, before we do that, I have to show one example with the exponential growth, and then we'll do that. Yes, of course.
Okay.
Yeah, so let's choose one with the exponential growth, and then we'll do the exponential decay, of course. So for the growth, bacteria, population, those grow exponentially. Bacteria, very good. So let's look at 14 on page 351. The count in a culture of bacteria was 400. after 2 hours, and 25,600 after 6 hours. What is the relative rate of growth of the bacteria population? Coming back, of course, this is the rate. N 0 is the initial, R is the rate growth, and T is time. Okay. So we are told we are looking at this bacteria growing so fast. Right now we counted, it's 400. It got to 400 in 2 hours. And then we go for lunch, we come back in 4 hours, we count them again, and we see 25,600. So what is given in this problem, first of all? So I want you to, when you look at the information, I want you to understand what the information is, and then decide what to do. So what am I given here?
Number and times.
Yes? Yes? Good. In other words, what else? What am I given?
Proportion.
Nope.
No. Final rate of change.
Okay. What else?
You get an initial, is a 400.
Yes,
Two.
400 is the initial. Initial would have been when t is 0.
Okay.
But I'm given the information that I don't know when they started. I'm assuming they started 2 hours ago, but I'm here now, and there is a sign on the Petri dish saying, you know, it started 2 hours ago. I don't know how many they had 2 hours ago, but I know that right now the count is 400, and I come back in 4 hours and I count them again, and they're 25,600. So what does this really tell me? In another way. No. I'm not saying that what you said is incorrect. It's perfect. But there is something else that we should be able to see when we are given such information. I am given two
Coordinates.
thank you, ordered pairs. I am given two ordered pairs. And which will be definitely and always the first coordinate?
Time.
Exactly. Time is independent. Time does not depend on what we do and how many bacteria are out there. So what is the first ordered pair then?
2 and 4.
That's it.
6 and 25, 600.
The reason is why is it so important to identify the ordered pairs? Is because each ordered pair says something about the model. It says that when I plug in the model what? What am I plugging in the model? 2. The output is?
400.
When I plug in the model,
6.
the output is?
25, 600.
That's crucial to understand. Yes, can I determine this without saying that they are two ordered pairs? Yes. And all of you said pretty much the same thing. But I want you to be able to identify that these are two ordered pairs. And what is very important is that this is always the time. And this is always the number. Okay, so the model, because we are talking about bacteria, I know that the number is the model is n of t equals n0 e to RT. I know that this must be the model I have to use. because this is the exponential growth model for bacteria and population. However, there are two unknowns. This is one of them. I have no idea how many they started with. And this is the other one. I have no idea what the rate is. Correct. So then that's the reason why I have to plug in the ordered pairs carefully and write how many equations. Because I have two variables, I'm hoping for two equations. Good. So please dictate the first equation.
It's gonna be in
400. That's what I said. We have to be able to identify what goes where. 400 equals N0. We do not have any information about N0. E. Yes, but T exactly. Once I put 400 here.
R times 2.
Exactly. It's 2 times R. So you understand how the ordered pair translates into this equation? Everyone? Okay, can anyone give us a second equation, please?
2, 5, 6 equals easy. 0. Yeah.
That's it. From these two equations, I don't know what I'm going to do, but I have to get N0 and R. Any suggestions? How to solve? This is a system of two exponential equations in two variables. We have never seen this before.
solve for one of them and substitute in the other.
I agree. What would you like to solve for?
R.
I can't.
Oh, and I guess, yeah.
I cannot solve for R here and then plug it in here because it would be kind of difficult.
Okay.
There are two options that I recommend. One, divide both equations. See what happens. This divided by this divided by this. That's one option. Second option, solve for N0 and then plug it in, which is basically the same thing with dividing two equations, but it doesn't matter. So, solve for N0, divide both sides by this, and plug it in here, which is exactly the same thing with dividing, but let's do just that. So from here, N0 equals 400 over e to 2r. And now I'm going to replace N0 in the second equation by 400 over e to 2r. So the second equation becomes 25,600 equals 400 over e to 2r times e to 6r. Is this clear so far? Okay. What do I do with these? Copy the base, and what happens with the exponents? Because the base is, careful, one is at the top.
Subtract.
Exactly. So I have 25,600 equals 400 times e to which power?
4.
Very good. I'm getting much closer now. This is an exponential equation. It's not fully cleaned up, however. Divide by? That's it. So I divide by 400. So 256 over 4 equals e to 4r. How much?
64.
Very good, thank you. And now I know how to solve. What should I do? Good. Because I can present e and 64 with the same base, I use natural log because the base is e, so I can simplify that side. So this is 4r equals natural log 64. 4r, the growth rate of this bacteria, natural log 64 over 4. And I need to approximate it. So natural log 64 divided by 4. Wow. 1.0. So what I recommend when we copy the growth rate, we should have at least 4 decimals. At least 4. So in this case, I would say 1.0397. .0397. Good. So I have R. I want to go back here and determine what? The initial number of bacteria. Very good. So N0 equals 400 over e to 2 times R, 1.0397. If you want to be fancy, you will use the entire previous answer to get the best approximation. So 400 divided by e in parentheses 2 times the previous answer. Instead of plugging it in and truncating it and so on and so forth, I just say 2 times the previous answer, and I'm going to get the best approximation possible. If I had truncated that, I would have not gotten 50. So what will you say the initial count of bacteria was? 50. So now can anyone give us, dictate the model? N of t equals 50 times e, 1.0397 t. After all this work, and given to us only 2 pieces of information, 2, 400, and 6, 25, 600, whatever that was, we are able to determine the initial size of the count, the initial count of bacteria, and also how fast is this bacteria growing. Okay, part B. What was the initial size of the culture? Okay. Part C. Find a function that models the number of bacteria n of t after t hours. Good. Find the number of bacteria after 4.5 hours. And the last question, when will the number of bacteria be 50,000? So let's find this one first. So 50 times E in parentheses, 1.0397. 1.0397 multiplied by 4.5 hours. We know how many we had at 2 hours, 400. We know how many we had after 6 hours, over 25,000. So it has to be somewhere between 400 and 25,000. Okay. Okay, 5,381. Okay. And final question, when will the number of bacteria be 50,000? What am I asked to do now? Very good. So I have 50,000 equals 50 e to 1.0397 t. Oh, yes, of course. Thank you. So 50,000 equals 50. Of course. So 1,000 equals e to 1. This is now a pure exponential function, and in a pure exponential function, I will use natural log in this case because of the base on the other side. So I have natural log of 1,000 equals 1.0397 t. So t equals natural log of 1,000 over 1.0397. Since in 6 hours it got to 25,000, I expect more than 6 hours. Okay, so natural log of 1,000 and divide by 1.0397. Okay, 6.64 hours. I want to add a question that is not in the book. When will the bacteria double its initial size? When will the bacteria double its initial size? What was its initial size?
50.
50. What do I mean by double 50?
101.
Good. So I'm asking, when will the bacteria be 100? This is also called a doubling time. Doubling time. How do I find when will the bacteria double its initial size?
You just do 100 equals 50.
Oops. Exactly. And then, yes, absolutely, I have to divide by 50. Oops, I didn't mean that. I jumped ahead, I'm sorry. So we have natural log 2, close and divide by 1.0397. Okay, so in approximately 0.7 of an hour.
On the calculator stuff.
Oh. Okay, so now let's look at the radioactive decay situation. Problem 20 on 352.